Okay, so it's around 6:13. So I think should start. So welcome to the seventh week of our live session, the course entitled Physics through Computational Thinking. Uh, Hello, I'm Javed Akhtar. So let's start. So in this week, the first thing that we will learn about how to solve any linear kind of system, coupled linear system, and, and also how to solve with can we extend this idea to non-linear system using this linear system idea. So uh, linear system equation, we can write down two linear equation as this: ax plus by and y dot equal to cx plus dy. So as you can see, these are two first order coupled linear equation. So what does this linear mean? So linear means that first let this equation, coupled equation, that we can write down in the following way: x dot equal to a of x. So x is what? X is x and y. So we are writing this both equation in a matrix form, and a is our a, b, c, d, and uh, yeah. So if as from this two, we can see that x dot, which means x dot y dot equal to a, b, c, d multiplied with x, y. So this will return our uh, this two equation. So from this we can go back to our original equations. So that is why this is so in that way we can write down any number of coupled equation into a single matrix equation form. Now what does the linear means here? So linear means that if if x1 and x2, these are solution of the given equation. So suppose this equation, it has two solutions, one is x1 and another one is x2. Then we we can write down another uh, uh, mm, form like c1 x1, c2 x2. So this will also be a solution. So that is what linear means. So it basically means that if x1 is a solution and x2 is another solution, then their combination, any combination will also be a solution of the equation. So we will go through, we will learn how to solve these kinds of equation, and we will also draw them in xy uh, axis. Now from this equation we can also, from this solving this type of equation, we can also learn how to draw phase space. So phase space means basically, so suppose we have a harmonic oscillator equation, that d2x dt square plus omega square x equal to 0. So this is our simple harmonic oscillator equation. And what does the phase space means? Phase space means the phase space diagram means the diagram of x and p, where p is what? P is m dx dt. Now we all know that for a simple harmonic oscillator, if there is no damping term, that then this x and p, they form an ellipsoid kind of thing. So we from this so from this solving this linear coupled differential equation, we we, we we can learn how to draw this kind of things. And in Mathematica, there are simple uh, command from which you can get this kind of phase space plots or similar kind of things. So let us proceed and uh, let us see how to solve this equation, this general equation. Now, we can write down this x of t as e to the power lambda t into v, where this v, it is not a function of time, so this is fixed. Now, this then what will be x dot? X dot will be lambda e to the power lambda t into v. Now, if we plug it here, then we will get to lambda t v into a e to the power lambda t v. So what does it, or what do we get? So we get a into v equal to lambda into v. So we can see that this is our eigenvector of a, and this lambda, it is our eigenvalue of a. Now how to calculate eigenvector and eigenvalue? So that we have basically everyone learned in simple differential equation or basic uh, mathematical physics course. So how can I get that? So a is basically a, b, c, d. Now if lambda is the eigenvector of a, eigenvalue, then we can write down a minus lambda I, determination will be 0. So you can write down a minus lambda, d minus lambda, here will be b and c, so this will be 0. So we can easily solve this equation. So let us proceed and solve it. So we'll get here a minus lambda, d minus lambda, minus b into c. So lambda square a lambda will be d, yeah, yeah, ad minus bc equal to 0. So once check if there is anybody waiting. No. Yeah. Now let us define this two quantity. Delta is equal to AD minus BC. So what is it? It is basically the determination of A, and let us define tau to be A plus D, which is what? Which is trace of A. So we can write down this equation as tau into lambda plus delta. So what will be the solution of this equation? So this lambda we will get to be tau square minus 4 delta divided by 2. So lambda 1 lambda 2, this will be plus minus of this. So these two are our eigen values of A. So lambda 1, it is tau plus tau square minus 4 delta by 2, and lambda 2, this is tau minus tau square minus 4 delta by 2. So if we get lambda 1 and lambda 2, then corresponding to lambda 1, we can calculate the eigenvector. So suppose this is v1, and for this also, for this eigenvalue also, we can calculate the eigenvector and let the eigenvector be v2. So if v1 and v2 are eigenvector, then we can write down the solution x of t as c1 e to the power lambda 1 t v1 plus c2 e to the power lambda 2 t v2. So this is the general way of solving coupled linear equations. So now we will go through one example to understand this fully in a clear way. Suppose we have these two equations. So the equations that we are given with is x dot equal to x plus y and y dot equal to 4x minus 2y. So, and we have to find the solution of find, and there will be an initial condition because this is a differential equation. So initial condition, suppose this is x0 y0 and the initial condition is 2, suppose minus 3. So this is our initial condition and these are our coupled equation which we have to solve, and after solving we have to find xt yt. So this is our task. So for that, what you have to do, first you have to define our A matrix. So A is 1 1 4 minus 2. Now we have to calculate the eigenvalue of A. So for that, what you have to do, so A minus lambda I, if lambda is the eigenvalue, then it will be 0. So it is 1 minus lambda. So what are the eigenvalues that we get? These are plus 2, and suppose lambda 2, this is minus 3. So for this eigenvalue, now what do you have to do? We have to calculate the eigenvectors. So let us first do for lambda equal to 2. Then what is the, if suppose eigenvector is v1, then what you will get? A v1 equal to lambda 1 v1. So let us plug in the values. Actually, I'm suffering from fever and cold, so I will not talk too much. So bear with this. So A equal to B is one solution. So our eigen vector is 1 1. So this is our first eigenvector. Now let us look at our second eigenvector. So lambda 2, this is minus 3, and for that, if v2 is our eigenvector, then we can write into v2 to lambda 2 to v2. So go ahead and calculate. So b is equal to minus 4. So if a is 1, suppose, then b can be minus 4. So these are eigenvectors and this is our eigenvalue. So now once we got our eigenvectors and eigenvalue, then what will be our x matrix? X at time t, it will be c1 e to the power lambda 1 t into v1 plus c2 e to the power lambda 2 t into v2. Now how can we get this c1 and c2? C1 and C2 we can get it from our initial condition. So x at t equal to 0, so we know that. So this is basically x0 y0. So this is 2 minus 3. So then what will be our, then we can write 2 minus 3 x equal to 0 equal to C1 1 1. So we can write now we have to solve just these two equations. So let us go ahead and solve this. So from this we can to write. So if we this will be 5C2 and this will be 5. So C2 will be 1, and if C2 is 1, then from this 1 we can get C1 is 1. So if C1 and C2 are 1, so the full solution of our x of t, so x of t is basically uh, e to the power 2t 1 1 minus 3t 1 minus 4. So x of t will be to the power minus 2t plus e to the power minus 3t, and y of t it will be e to the power 2t minus 4 e to the power minus 3t. So this is the general way of solving any linear coupled differential equation. So first we have to define them in terms of matrix. Then from matrix we have to calculate the value and eigenvector. And from that eigenvalue and eigenvector, we can calculate. So we can finally express how x and y depend on time. So let us try to draw its xy diagram. So as you can see, so let us try to draw that. So as you can see, so there are two orthogonal lines, and along one line, so there is exponentially increasing. So exponentially increasing, and this is 1 1. So 1 1 will be around something around this, and from that it is exponentially increasing. So it will be like this, and from 1 minus 4. So how can be 1 minus 4? So this is not correct. So 1 1 will be this, around this, and 1 minus 4, uh, this will be somewhat around this. And for 1 1, it is exponentially increasing, so it will kind of go outside. And for 1 minus 4, it is exponentially decreasing, so it will kind of go inside. And if we draw any other face portrait, so it will first go inside and then it will go around this. Similarly here also, similar kind of things will be also observed here and here also. Yeah. So this is the general way how to draw this mm, stream plot kind of thing. So this thing we can do easily in Mathematica, but for a hands-on feeling or hands-on experience, I just show one detailed example of how we can think of how we can think of this streamlines. So this equation, how we can solve this in Mathematica. So let us go ahead and do. So our equation is x plus y, and second one is 4x minus 2y. Yeah, so as you can see that this is this uh, here you can see so that there are two, so this line corresponding to this 1 1, and this line corresponding to this 1 minus 4, and there are other stream flows which will follow this. So in Mathematica you can do this easily just by just typing down this stream plot command, but yeah, so you can also try different things also. So let us do just this one. Yeah, so this is for this y minus x. So this is basically the equation of simple harmonic oscillator, and we know the English of simple harmonic oscillator. This x and p diagram, there will be a center, so there will be circles. So and this radius of the circle that are determined by the energy of the system. So each circle correspond to a trajectory of a fixed energy. So different circles of different areas, they indicates to different energies of this harmonic oscillator motion. Yeah, I will take just 1 minute break. Okay, so this kind of things when we have one eigenvalue to be negative and another eigenvalue to be positive, so these are known to be saddle point. So when can this saddle point appear? So we have seen that this lambda 1 2 that can be written as tau plus minus. So as you can see here that if delta is negative, then whatever the value of tau, so yeah, if delta is negative, then whatever the value of tau, we have this tau 1 will be positive and another will be negative. So this is the case for saddle point. So this kind of trajectory are known as, so when you have this kind of trajectory, then the origin is a saddle point. So because for one direction we have this system to uh, to come zero, but for another direction it will go to infinite thing. So that is why around one direction it is minimum, but around another direction it's kind of maximum. So that is why it is called saddle point, and we have this saddle point whenever delta is zero, then we will get our saddle point. Now let us look for our other cases. What will be the case now if we have both the eigenvalue to be positive? So suppose lambda 1 lambda 2 both are positive, and for a moment suppose that lambda 2 and both are greater than 0. So lambda 2 is greater than lambda 1. So then in that case, so as usual we will have two axes. So suppose this is one axis and this is other axis. So we will call this slow and this is fast. What does this slow means? Slow means whatever which between lambda or lambda 2, whichever is small, for that eigenvalue the corresponding eigenvector direction is denoted by the slow eigendirection. Slow eigendirection. So it is for here lambda 1 and this is for lambda 2, and we can see, so since both are positive, then it will point towards out of equilibrium, out of center. So it will point like this, and so whatever so this is regarding the direction and all that, and now the trajectory typically approach the origin tangent to the slow eigendirection. So uh, and so how we can define the other trajectories here? So we can define like this. Yeah, so it will be okay. So this is both. So this will be yeah, in this direction, and this will be in this direction. So this is the case of unstable node. This is known as unstable node. When both the eigenvalue are positive, so then we will have a slow eigendirection, fast eigendirection, and any trajectory it will approach the tangent to the slow eigendirection, as you can see here. So around this 6 point, so it is tangent to the slow eigendirection, as you can see here, for every trajectory, for every other trajectory also. Yeah, and if both of them are negative, then Suppose this is the case, lambda 2, lambda 1. Uh, so I have just make a mistake here, so it will be this. So if this is the case, then again we will have our slow eigen direction. Suppose this is slow, this is fast. I'm just drawing randomly here because I'm just assuming if that is the case, what is going to happen. So then it will be slow, it will be fast. Now only the difference will be in the direction of arrow because both are negative. So ultimately it will equilibrate and it will come towards the center point. So arrow in this direction, and similarly for this curve arrow will be in that direction. So this is known as stable node. So this is the case of stable node. Now what will happen if the eigen values are complex number? So suppose this lambda 1 2, this is half into tau plus minus tau square minus 4 delta. Now what will happen this if this tau square minus 4 delta it is less than 0. So then we can write down this lambda 1 2 as alpha plus minus I omega, where this alpha it is tau by 2 and omega this is half 4 delta minus tau square, because tau square minus 4 delta less than 0, so you'll have to take a negative sign common, and that will be our I factor, and the rest of the term will be our omega term. So if that is the case, then then we can write down our general solution as this. Now since this lambda and lambda both are complex, that leads to C1 V1 and C2 V2, they can in general be complex also. So the solution xt, it will contain terms of this kind, e to the power alpha plus minus I omega t. So which means, so this e to the power I omega t, that we can write down as sine plus cosine omega t. So this is the general form. So the xt solution, it will contain e to the power alpha t sine of omega t and e to the power alpha t cosine of omega t. So it will contain both. So now if this alpha, which is the real part of lambda, so if this alpha is less than 0, then we will have a oscillation, and this if alpha is less than 0, then that means we have an oscillation, decaying kind of oscillation. So this sine square cosine square theta, this is 1. Now if alpha less than 0, then we will have this kind of decaying thing, and if this alpha, so we will have this decaying oscillation. And on the other hand, this alpha, if it is greater than 0, then we will have an oscillation or an which will increase with in amplitude. So this we can call as stable spiral, because ultimately eventually it will come down to the equilibrium point or center point. But here, so if it starts from here, then it will amplitude will increase and it will go like this. So it is in this direction, and here it is. Yeah. So this is growing oscillation, and this kind of thing are known as unstable spiral, because ideally it will blow up and it will go to infinite. So, and if this alpha is 0, then we will have just a pure oscillation. So this is a center. This is alpha 0. This is for, these are three cases. This is case 1, this is case 2, and this is our third case. Now, with all these ideas, so let us generalize the whole thing. So we have our tau and delta diagram here. So delta, tau, and so if delta less than 0, then what is it? So this is the general idea. So from looking at the value of this tau and delta, we can easily tell where will be our fixed point. So what type of fixed point we have. So is it saddle point, or is it center, unstable spiral, or stable node, unstable node? All of this, that everything we can conclude from this. No, this is all good. Like we know how to solve this any general kind of linear equations. Just plot just a simple 2, 3 just to get you the feel. As you can see here, just this xy. So we have this kind of. So this is another equation for which we have this kind of. So this is. So these are non-linear equation. So can we generalize this linear equation idea to non-linear equation? That we will learn now. So suppose we have a non-linear equation of this kind. So can we implement our linear equation idea to this? So this x dot equal to f of xy, y dot equal to g of xy. So this equation they can contain any nonlinear terms. And suppose x dot y dot y star. So this is our fixed point. So what does this mean? So it means this is 0, and this is 0. Now, suppose we disturb the system around fixed point. So we perturb and and this how much disturbance we give, that is denoted by u. So now we have to see at the dynamics of u and v, like with time how it will change. Will it come back to x dot y dot, or it will just go away? So for this, can we generalize our linearization idea? So let us do that. Go ahead. So what will be our u dot? U dot will be x dot, because this x star, this is fixed, so derivative of this will be 0. So, and this is simply this x and y. X we can write as u plus x star, and this is v plus y star. Yeah. So now this from Taylor series expansion, we can write this as this del f del x at x equal to x star u plus del f del y equal to y star v, and then we will have higher order terms, quadratic, like u square uv order of this. uh, so this is 0 because this is x dot, this fixed point. So ultimately we can write down this as u del f del x at x equal to x star v del f del y at y equal to y star, and we have here order of u square v squared uv. Fine. Then what will be v star v dot? So similarly, if we go ahead and do similar calculation, so it will be g of u plus x star v plus y star. Then we will get u dg dx at x equal to x star v dg dx dy at y equal to y star plus order of u square v square uv. So from this u and v, so this we can write down as this u star v star equal to a b c d uv plus order of v. And what is this abcdr? So a is basically du dx at x equal to x star, b is df dx. Yeah. So df dy at y equal to y star, c will be dg dx at x equal to x star, and d will be dg dy at y equal to y star. Then we can see that if this term is not big enough compared to this, then we can see that we can safely apply the linearization. And so but there is always and kind of alarm when we are in borderline case. So what are the borderline case? Borderline case means when we are at the center, or when we are along this line or along this line, then it is good to check with original equation what we have. But whenever we are deep inside any phase, suppose we are within this or saddle point here, now the nature of the point that doesn't change with the linearization tool. But in case of this center, it may happen that with the linearization idea we get it to be a center, but when if we, without applying the linearization of this non-linear equation, if we take our equation and fully with Mathematica, if we plot the stream plot, then it may happen we may get unstable spiral, stable spiral, or even center. So that is the case. So this matrix, so this is called the Jacobian. So what we have to do, we have to calculate the Jacobian of our given equations. Okay, so we will continue after 2 minutes. 2-3 minutes. Okay, so let us look at some example. So suppose we have these two equations. Suppose you can see here, yeah, 0, 0. This is one stable, like this is a fixed point, as you can see here. Now, and you can see here this is a nonlinear equation, this and this. So how can we? So let us implement the idea of linearization. So first you have to evaluate the Jacobian matrix. So Jacobian, this will be 0. This will be 1 minus 3y square, and add to y equal to 0. This is minus 1. So 2y into 0. So this is 0, 1, this one 0. This is the Jacobian matrix. Then what will be delta? Delta will be uh, 0 into 0 plus 1 to 1, and tau, this will be 0. So tau is 0 and delta positive. So So delta positive and tau 0. This means along the center. So what we get? So around 0 we should get this kind of so let us so since this center is a borderline case, so let us have a look mathematical. What does this stream plot gives to this equation? So what is the equation? Equation is y minus y cube, and here we have minus x minus y square. So let us just check if it gives center or not. Yeah. So as you can see here that around 0 it will give us a center. So since this whenever we have these borderline cases, we have to check for if this linearization in nonlinear equation gives a correct result or not. So in that case, in this case, we have a result which satisfy that, but there may be some example where mm, this will not satisfy, and both of them will not be consistent with each other. So let us look at that kind of example one. So let us look at the example. So as we discussed in class, so if these two are equations like x dot equal to minus y plus ax plus x square plus y square, and y dot is equal to x just x plus ay x square plus y square, then now we have to construct the Jacobian. So the 0 0, as you can see from here, 0 0 is a fixed point. So the Jacobian around 0 0, it will be let me write down. Yeah. So this is the Jacobian, and similarly here delta will be 1, tau will be 0. So this is the center. So ideally we should get this kind of plot, but I can see here that there is no dependence on A. So let us go to Mathematica and check if it always gives us center or not. So, so let us first define A to be 1. and write down this equation. So it will be minus y plus ax multiplied with x square plus y squared. So this is our first term. Second term will be similar kind of thing. So we just copy this. So this will be a y and this is positive x. Yeah, so around 0 it has center. Now let me clear all this thing. Yeah, now define a to be minus 1. Yeah, for a equal to minus 1 also around 0 it is center. And let me check with, let us check with a equal to 0. Yeah, so here also around center, around 0 it is center. But if we look at one or these cases, yeah, so it is center around 0. But if we have a larger value, then it is it is spiral. So and so this is stable spiral because it is coming down to 0. And so that is why we cannot always predict with the help of Jacobian how the how the what is the behavior of the fixed point. So this is the general idea. So you can look at other examples also of this kind, and you can check how these things. So you can do this with different kinds of examples also. Just you have to write down the stream plot command. Now we will learn. Now we'll so basically we as you have seen here from the phase diagram from the T tau delta diagram that uh, the half of the space, half of the diagram space. So you can see here that almost 50%. So if we take any random matrix, so this matrix, suppose we take a very large number of random matrices, suppose 10,000, 5,000, 10,000, 100,000, 1,000 matrices. So, and the elements of the matrix, like the ABCD, they are randomly chosen. So it is expected that around 50% of time we will get saddle point. So this process of dealing any deterministic, so of dealing with any mathematical equation which underlying process is deterministic, so that we can easily handle with random numbers generated with random numbers. So this is the idea of Monte Carlo simulation. So in what is the idea of Monte Carlo simulation? So we assume we will choose the elements of the matrix to be random, to be truly random, unbiased element, and we will produce in almost 10,000, 5,000, 100,000 number of matrices of different random numbers, and from that we will calculate the how much saddle point how much time we get the fixed point to be a saddle point, or we get it to be unstable node, stable node, so that we can check. So let us go ahead and do this in Mathematica. Okay, so this is the command. So I will explain what we are doing here. So this A list, B list, C list, and D list. It is basically the element of the matrix, and we are choosing it from a random real. So what does this random real command do? So let us check. So random real. If we don't, so it will give us every time we will execute, it will give us defined number, and we can specify the range here. So 2 means it will give from 0 to 2. Again run again. Yeah. So here we are doing this random real minus zero point 0.5. So what does this mean? So random real will give us from 0 to 1, and we are subtracting minus zero point 0.5. So it will give us from minus zero point 0.5 to plus zero point 0.5. Yeah, as you can see here. So by this way, we will create a list. So what is a list? A list will basically contain uh, the a element of the matrix for I. It will run from I equal to 1 to n mat. So suppose if n mat is 1000, then this a list will contain thousands of random number, and similarly b list will also contain this thousand of random numbers. Similarly C and D, all of them. Now we want to see uh, what is the fraction of this saddle point. Now, what will how can we calculate the fraction of saddle point? So for that, we have to first calculate the delta and tau. So what is delta? So delta, we know that AB minus BC. So this A list, D list, and minus B list, C list. So it will create the list of these uh, deltas of different matrices, and similarly tau will also create a list of this, and this disk list. So it is basically the element in the square root, like tau square minus 4 delta. Now, what does this unit step does? So let us look here. So if we have a minus number, then it will give us 0, and if we have a positive number, then it will give us 1. So whenever within the unit step we are having a negative number, it will give us 0, and whenever we having a positive number, it will give us 1. So how can we calculate the saddle point? So let us go back to our phase diagram. So we can see here that saddle point, when saddle point will happen when this delta is negative, and whenever this delta is negative, we will have saddle point. So what you can do here? So what you can do? We can create infinite like millions of matrices, and for millions of matrices we can calculate 1 minus unit state of saddle point. So whenever the saddle point, one minus unit step of delta, as you can see here. Yeah. So 1 minus unit step of delta. So whenever this delta is negative, it will give us 0, so it will be 1. And whenever this delta is positive, then this will be 1 and this will be 0. So we want to calculate the number of times whenever the delta is negative. So for that, whenever the delta is negative, this 1 minus unit step of delta, it will give us 1. So this total command, it will count how many times we will have this 1 minus unit step of delta to be 1. So it will calculate count this, and it will divide this with delta list. So what is delta list? Delta list is basically uh, the total number of matrices that we have taken. So because the length of delta list is equal to the length of matrix, because for each matrix we will have a delta. So this will give us the fraction of saddle point. Now how can we calculate the fraction of stable node? Suppose unstable nodes. So for unstable node, what are the conditions that we need that needs to be satisfied? For unstable node, this delta has to be greater than 0, first condition. So let me write down that. So the first condition is delta has to be greater than 0. Second condition, tau square minus 4 delta greater than 0. Third condition, tau greater than 0. So we have to, so this, all three of them should be simultaneously satisfied. So how can we write this in code? So we have to count like total. So what we have to do, to unit step. So this has to be greater than 0. So unit step of delta list. So since all of them has to be simultaneously satisfied, so it will be multiplied with unit step of tau list. So this we have incorporated, this we have incorporated, and this is disk list multiplied with unit step of disk list. So we have to count this whenever all three of them are 1. So that will give us the unstable node point, and we have to count how many times we have this unstable node point, so that we can, in that way you can calculate unstable node. So how can we calculate the stable node? So for stable node, delta has to be greater than 0, but other two conditions, the second condition should also be satisfied, but third one, tau should be less than 0. So whenever this, we have this delta greater than 0, tau square minus 4 delta greater than 0, and tau less than 0, we have stable node. So let us see what is the fraction of stable node also. So tau less than 0. Let us define here. So this will be this tau list. So it should be negative tau. That means we have to write down here 1 minus. Yeah, and this will be fraction of stable node. And here we also see fraction of stable node. We want to see they should be more or less similar, fraction of stable node and first fraction of unstable node. So just run this. Yeah, as you can see here that almost 50% of time we will have the saddle point, and around 0.01, I mean 0.1%, 0.925, 0.965. So if we increase our n value to be more, so like if we have our n value to be 10,000, then as you can see, the result will get better. The more number of matrices we have, the result will be better. So, but there is other catch also. If we take very large number of matrices, then it will take a little bit of longer time to run or to execute our code. So as you can see here that it is still running. So we have to just wait for a few seconds, I guess. Okay, so let's just quit this. And so this is the general idea. Like you can do estimate other cases also. Like you can estimate the number of stable spiral. So what are the conditions for stable spiral? For stable spiral, you have to have delta greater than 0, this tau square minus 4 delta less than 0, and stable spiral, this tau should be less than 0. So in last two cases, you have to import this 1 minus unit step, and for delta you will have to invoke this in only unit step. So from that you can easily calculate this things. So let us go ahead and do some more examples of this Monte Carlo simulation. So we can easily calculate any integral from this Monte Carlo simulation. So let us go ahead and do that. So we know that Suppose you have a standard integral like this. So dx by 1 plus x from 0 to 1. So what will be the solution? This is basically ln 1 plus x, and if we put limit here, then it will be ln 2 minus ln 1. This is 0, so it will give us ln 2. So how can we do this with help of this Monte Carlo simulation? So what we can do, we can invoke the value of x from this 0 to 1 very large number of times, and from that we can calculate the we can sum them and we can take them in, and this process we can do a lot of times. This process we can repeatedly do a lot of time, and we have to take the mean of the means. So let us go ahead and check this. So I will upload this both the files, this practice file and uh, week 7 file. 7c here. So this is this 1 by 1 plus x, and this will take from this random number, and we will take its mean, and then we are again mm, doing a table of this mean value, and then we are taking the average of this means. So let us go ahead and execute. So and we will do that. So the outside table, that is for this how many numbers we are taking, so how many random samples we are taking. So for 2 to the power k, that means first we are taking 2 to the power 5 numbers, then we are taking 2 to the power 6, 2 to the power 7, and so on. So let us go ahead and execute this. So it is running. So you can see here that if we run the code, then we will have, so this is our number of number of samples in our random list, and this is the value we get. So ln2 is approximately 0.69. So as you can see, if we increase the number of element, then our we can plot the data here. So as you can see, as we increase the number of element, as you can see that, so it will converge to ln2 value. So what you can do, we can plot the error list. So for error list, what you can do, so from this mean value, we can directly subtract the ln2 value. So as we have done here, so we have subtracted the log value, and so it can be positive or negative after subtraction. So that is why we are taking the absolute value, because we want to know the amount of error. So in that case, positive or negative doesn't matter. So that is why you have taken the absolute here. So this is the absolute command, and if we plot that with the number of element, as you can see, as we increase the number of element, we can see that the error is decreasing quite fast initially, and then it is converging to a range. Now let us do for another integral. So this is for another integral. So we know, so this 0 to 1 dx by 1 plus x square equal to pi by 4. So from this we can estimate the value of pi using Monte Carlo simulation. So pi will be 4 by 1 plus x square dx 0 to 1. So the function will be basically this. In previous case our function was this 1 by 1 plus x. Now our function is 4 by 1 plus x square. So let us look at the mathematical code. So this is 4 by 1 plus x square, and again you can see that it is converging, and if we plot that error, we can see that the error also converging. At first error is decreasing with number of element, and soon it will settle down to a value. So let us now look with other things. Yeah, so this integral. So there are in this way you can calculate any kind of integral using Monte Carlo simulation. So suppose you have this integral bx by 1, no, so that we have done already, ln x by 1 minus x dx 0 to 1, it will give us minus pi square by 6. So let us check if we get this with the Monte Carlo simulation or not. So this is our function ln x by 1 minus x. We have defined our function here, and this is the similarly we have written here. Whatever we have written here, this xi is random real. That means xi is taking value from the distribution which is random real. So here you can take value from any other distribution also. You have to just specify it as a distribution here. So as a example, you can take value from a distribution like normal distribution, like Gaussian kind of distribution, which has mean of 0 and variance of 1. So any kind of thing from anything, you can take your this distribution. So once we get the x's, so from that you can calculate this. Uh, so as you can see here, that this is our. Let's go ahead. So this is our value. So as you can see, this is 1.644. So this is quite approximately equal to the this pi square by 6. So as you can we can see that using this Monte Carlo simulation, we can easily or we can effectively calculate this any standard integrals here. So other things, so what you can do, so we can calculate pi in other ways also. So one way of doing that, so let me illustrate this by illustration. So suppose we have this box, and over which uh, so let me draw this in. So and this is, so this is a machine which will drop marbles on this surface on this cross section area, and here we have one square of length 1 meter, and we have another circle of radius 1 meter. So what is the cross section area of this? So this is pi r square, this is pi, and cross section area of this 1 into 1, so this is 1. So what you can do, uh, we can use the Monte Carlo simulation to estimate the pi here. So this thing, it will drop marbles randomly over this plane. So as the way we're choosing that random number from a distribution, so in that way it will pour marbles randomly over this plane. Now the number of marbles accumulated on this on the square surface and this circular surface, it will be proportional to the cross section area of them. Now, so what you can do? So we can drop infinite, very large number of marbles. So suppose we drop 5,000 marbles over this. So randomly. So and from that we estimate, we calculate the total number of. So suppose A is the number of marbles on circular drum, and B is the number of marbles on square drum. Now, this A and B, these are proportional. This is proportional to pi, and B, this is proportional to 1. So if we take the ratio A and B, so it will be proportional. So it will be, so the proportionally constant is same. So it will effectively lead us pi. So if this is another way of estimating pi using this Monte Carlo simulation. So that is it for today's lecture video. So in the next lecture video, we will continue more about this. So we will talk about